Welcome to the next scale model, 1 to 1 trillionth. We'll call this the Pico scale model. Pico coming from Spanish, meaning a small balance. So now we're enlarging everything by a trillion times, and we're inside of the atom. Previously, we were looking at a hydrogen atom, for example, that was about 0.1 meters wide. Now the hydrogen atom is 100 meters wide. So if the lighthouse is the nucleus of the atom, we're standing about 50 meters away. This is about the edge of the hydrogen atom right here. So at this scale model, the uranium atom is about 340 meters wide. So I've moved back about 170 meters from the lighthouse, which we'll call the center of the uranium atom. And this atom is about 3 times the size as the hydrogen atom. And so the scale model is quite a challenge because atoms are a little bit too large to show anything. And as we'll find out, the nucleus is still really, really tiny. It's still hard to see. Previously, we had thought of atoms as just billiard balls, solid objects. They were indivisible. They were fundamental things that were solid. There was no breaking up or there was no space inside. But as we know now, atoms are not solid. They contain a lot of empty space in between. At this scale model, we need calipers to show you the nuclei of atoms. That's how small they are. And here I have a little egg holder so that my nuclei don't go flying away. And these are for 3 different atoms. We have hydrogen, helium, and uranium-238. So hydrogen has a single proton, and that proton here is only about 0.085 millimeters wide at this scale. This is helium, so we have 2 protons and 2 neutrons. So that nucleus is a little bit bigger. And uranium-238, imagine this was packed with protons and neutrons. You have 92 protons and 146 neutrons. The atom has just a vast amount of emptiness to it. It's like we've stumbled into another void, and we've seen these voids before going into the macro side of scales. We've seen the distance between stars, for example. It's very hard to kind of create a scale model for that. For example, when we went to 1 to 1 trillion, the sun basically just became a grain of sand. And the next closest star was about 40 kilometers away. So you didn't see a lot of detail, and there was a lot of emptiness. And it seems like the 1 to 1 trillionth, which is the same ratio but going the other direction, we find ourselves in a similar kind of void where particles are also really tiny. We don't see any detail yet, and there are a bunch of other particles that are still way too small to see. They're almost invisible. So it's not obvious to me how the scale models going into the micro world would continue. So this is where we stop. So we've gone down 4 rungs on the ladder, even though we know that there are many rungs that keep going down, down, down. How far they go, we don't know. But in order for a scale model to be interesting, it has to show some kind of object in relation to something else. And even at this scale model, it seems a bit empty. In a previous video, when we were climbing the ladder of scale, we talked a little bit about, well, how far does it go? It's trending towards infinity. Is the universe finite, or is it infinite? And there's a kind of a similar situation going when you go down the ladder in the micro world. It's trending towards something. So it's trending towards something that has no size, something that is just a point, or something that we sometimes call a singularity, where basically you have something that can exist, but it has no size to it. And if you think of something that is infinitely large, it exists, but it also has no size, because infinity is not a number. It's not a, can't measure it. And so it's curious to know how far the universe goes down in the micro world and whether that's infinite or not. It would seem strange if there's a limit on this ladder on the top, but not the bottom, or vice versa. You would think the top and the bottom would both be consistent. They'd both be infinite, or they'd both be finite and bounded in some way. I am slightly more comfortable with a finite universe, both in the micro and the macro. So it would be, if the universe were like a movie screen, we can step back and then we see that there are some edges to it. It's a finite screen, but then if we move up very close, we see pixels. And if you go below the pixel, you're not in the movie anymore. And now it's not defined. Another point is whether the scale we live at is special in any way. Hard to say, but it does seem like if you're on the extremes of these scale models we've looked at, certainly things seem most complex in the middle. And towards the edges, for example, in the micro world, these building blocks are all identical to each other, and the variety is not that great. And then if you go in the macro side, we're looking at the universe and looking at trillions of galaxies all strewn about like in a bubble bath. The complexity also seems less than what the complexity I'm surrounded with when I'm closer to actual scale. Another neat trend in these scale models is that they were tied to history and technology. As we created instruments, and as we created new technology, we were able to open new doors into the macro world and into the micro world. And this trend hasn't stopped. We've historically often thought we've reached a plateau, and our knowledge is basically not going to expand much more. But so far, that's not the case. So thank you for spending some time with me on these scale models. It was a lot of fun. And I hope to see you in a future video. Thanks. Cheers.